Hello there, and welcome back to the Sleepy Science. The lab lights flicker gently overhead, humming with the weight of discovery. You're not exactly sure where you are. It smells faintly of chalk dust and coffee, and the blackboard in front of you seems to go on forever. There's a scribble in the corner, Psi X, like a whisper from the quantum world. You take a hesitant step closer. Around you, nothing feels solid. Particles shimmer, entangle, disentangle. One of them may or may not even be there at all. Time feels wrong. Distance, irrelevant. Up ahead, something invisible tugs on your ankle, like a signal from far away, though nothing seems to have moved. Welcome to quantum entanglement, the part of physics that unsettles even the most seasoned minds. And fair warning, you probably won't survive this with your common sense intact. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment with where you're tuning in from and what time it is there, just so we know how far across the entangled world this sleepy story travels. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're drifting through the earliest days of quantum mechanics, where physicists still smoked cigars in their offices and argued fiercely about what the heck reality even meant. It's the 1930s, and somewhere in Germany, a young physicist is furiously writing equations that suggest particles, tiny little bits of matter, can become entangled. Like cosmic dance partners who never forget each other's steps, even if they're flung across galaxies. You change one, the other changes too, instantly. Without delay, no signal sent, no light required. Einstein reads about this and immediately hates it. To him, it reeks of incompleteness. If something over here can instantly influence something over there, then what happened to the universal speed limit? Remember, nothing, absolutely nothing, can travel faster than light, not even your panic attack when your phone dies at 3%. But entanglement, it just laughs in the face of that rule. And Einstein, who helped define that speed limit in the first place, doesn't find it funny. He calls it Spukhaft Fernwirkung, spooky action at a distance. And yes, he actually used that word, spooky. But let's back up. What even is entanglement? You picture two electrons born from the same event, maybe a decaying atom somewhere in the heart of a dying star. As they drift apart, something strange happens. If you measure the spin of one electron, the other's spin is instantly determined, even if it's light years away. It's as if the universe knew the answer all along and just kept it hidden until you asked. Or worse, it didn't know until you asked, and then retroactively decided the outcome. Either way, your head hurts, and you want your blanket. This idea haunted scientists. At the core of it was a question: is reality local? In normal, comfortable physics, things interact locally, meaning only things near each other can influence one another. You can't punch a wall in Paris and expect your knuckles to hurt in Peru. But entanglement says, maybe you can if you're a photon. Now imagine a game. You're blindfolded and handed a pair of socks, one red, one blue. You mix them up and send one to a friend on Mars. Later, you pull off your blindfold and see the red sock. Instantly, you know your friend has the blue one. That's not spooky, right? It's just logic. But here, where it gets weird. In the quantum world, the socks don't have colors until you look. They're in a weird, wobbly superposition of red and blue. And only when you peek does the sock decide on a color. And somehow the one on Mars instantly decides, too. Even if Mars is 12 light minutes away, the decision happens faster than light could travel. Now you see why Einstein's forehead vein twitched. But here, the unsettling twist. No one, not even the people who make a living off this stuff, completely agrees on what's going on. Historians still argue whether Einstein's main beef was about realism, the idea that things have definite properties whether or not we observe them, or about locality, the idea that objects are only influenced by their immediate surroundings. Either way, he teamed up with two colleagues, Podolsky and Rosen, and in 1935 they published what became known as the EPR paradox. They hoped to prove that quantum mechanics was incomplete, that it needed hidden variables to explain this bizarre behavior. Spoiler alert, it didn't go quite as they hoped. But let's linger for a moment in that mid-century lab haze. Typewriters clack, chalk scrapes. There's this uncomfortable vibe in the room, like everyone knows they're poking at something far bigger than themselves. And every time they close the equations, the answer isn't satisfying. In fact, it's downright creepy. Entangled particles don't send signals. They don't beam messages through wormholes or ride tachyons. They just are linked in a way that makes the very idea of space feel optional. One fringe tidbit. In the 1970s, a Soviet researcher named Yuri Danilov speculated that entangled particles could be used to communicate with submarines under the Arctic ice cap. He didn't get very far, partly because the math didn't check out, and partly because nobody could explain how the information would travel. But it's cute, right? Quantum Cold War phone calls. You pull your blanket up to your chin. The room gets quieter. The idea that particles could be entangled across light years, that they could defy space itself, isn't just unsettling. It forces you to question whether space, time, and causality are really as ironclad as they feel. And you haven't even met Bell yet. You lean deeper into the mystery, blinking slowly as you follow those ghostly particles drifting apart, still bound to each other by something no one can quite define. They're like dancers twirling away in perfect synchronicity, never breaking rhythm, no matter how far they spin from one another. This is quantum entanglement in its purest form. Two particles, birthed from the same quantum process, locked into a single shared fate. No matter how far they travel, they remain coordinated. Spookily so, it's not just charming, it's chilling. You picture it with photons, those little packets of light that sometimes act like waves, sometimes like particles, and always like they're up to something. When you entangle two photons, say, by forcing them through a crystal that splits their paths, you've effectively tied their quantum states together. Measure the polarization of one, and you instantly know the others, even if it's halfway to Alpha Centauri. Not because they were pre-programmed like synchronized watches, but because their states didn't actually exist in any meaningful way until you observed one of them. At that moment, the universe commits, and not just here, but there too. The twist, the particles don't carry instructions from the start. If they did, their behavior would line up with something called local hidden variables, predetermined properties hiding under the hood. But experiment after experiment shows, no dice. These twins don't just mimic each other, they respond to each other, in real time, and somehow without transmitting a signal. It's like opening one fortune cookie and watching the other one, on a different continent, snap open and reveal a matching fortune. Not similar, identical. You try not to think about the implications, but your brain won't stop whispering. If the particles aren't preloaded with information, and if they're not sending messages, then how? How does the second particle know what the first one just revealed? And if that communication or influence or whatever it is happens instantly, then doesn't that mean information is traveling faster than light? It's a whisper of heresy in the Church of Physics, but the entangled particles just spin silently, unbothered. There's a simple experiment you'd love to try if only you had $1 billion lab and a laser cooled to near absolute zero. You create two entangled particles and fire them in opposite directions. You then measure the spin of one particle at a specific orientation. Instantly, the other one's spin is set, even if it's miles away. This has been tested, repeatedly. The results are statistically airtight. Measuring one particle really does affect the outcome of the other, faster than any signal could have traveled between them. But, and here's the sleepy paradox, it still doesn't let you send usable information. No messages, no Morse code, just statistical ghosts. Still, that doesn't mean entanglement is fake. Far from it. The phenomenon is among the most experimentally verified quirks in quantum physics. It's real, it's weird, and it's unstoppable. Physicists have entangled photons, electrons, atoms, molecules, even tiny diamonds. In 2017, Chinese researchers successfully transmitted entangled photons between a satellite and a ground station over 1,200 kilometers apart. That's not just theoretical. That's Star Trek stuff, except real and less shiny. Your mind drifts further back, to the dusty halls of the Solvay Conference in the 1920s. That's where Einstein, Bauer, Heisenberg, and Schrödinger all squinted at the same equations and came away with entirely different nightmares. Schrödinger, famous for the unfortunate cat, was also the one who coined the term entanglement. He recognized it as the defining trait of quantum mechanics, the one that makes you whisper "what?" into your cereal bowl. Unlike classical physics, where two systems can always be described independently, entangled particles can't be. Their description is shared, like a password written in two halves. And here's the kicker. Once two particles are entangled, they can stay that way indefinitely as long as nothing interferes. A passing cosmic ray, a random vibration, even a gust of thermal noise, any of it can disrupt the fragile link. That's why most real-world entanglement experiments happen in labs with absurd precautions. Cryogenic temperatures, vacuum chambers, optical traps. It's like building a dollhouse on a trampoline while the wind howls outside. Yet even with those precautions, decoherence looms. That's the term for when quantum systems lose their weirdness and settle into boring classical behavior. Basically, when reality gets tired of being strange. And who can blame it? Some experiments have shown that entangled states can survive over large distances and long times, defying classical expectations. One quirky tidbit. In 2008, physicists claimed to observe entanglement between two diamonds separated by centimeters, large enough to be seen with the naked eye. This was a big deal because diamonds are not subatomic. They're macroscopic, tangible, and generally not considered whispering partners in quantum mysteries. Yet in this experiment, vibrations in one diamond seemed to match the others precisely, not due to vibrations traveling through the table, but possibly through entanglement. Could bling be spooky? Apparently. Still, there's an uncomfortable truth lurking here. No matter how solid the experimental data, we don't have a definitive explanation for how this connection works. Historians and physicists still argue whether entanglement reflects a deeper, undiscovered structure in the universe, or whether our current understanding of space and time just isn't the final version. It's like we're watching a puppet show, convinced the strings must exist, but every time we reach for them, they vanish. Even when entangled particles are separated by light years, no known force seems to mediate their connection. There's no medium, no tunnel, no warp bubble, just an eerie, instantaneous link that scoffs at Einstein's speed limit but somehow never violates it in any useful way. It's like a magic trick that breaks the rules, but only when no one's watching closely enough to catch it. So here you are, lying still, watching two particles spin in opposite directions, forever synchronized, forever apart. You wonder, is the universe secretly held together by threads of entanglement? And if it is, what happens when one of those threads breaks? Do we notice? Do we blink? Or do we dream briefly of a world where distance doesn't matter and time has nothing to say? You close your eyes and the particles keep dancing, quieter now, fading into the velvet black. Einstein, for all his warm smile and tousled hair, was not here for your quantum nonsense. As you recline deeper into the strangeness, you find yourself peering over his shoulder in 1935, eyebrows furrowed, as he scrawls equations with an intensity bordering on indignation. To him, physics should be clean, predictable, and elegant. And yet, this new quantum theory smells like chaos wrapped in probability, dripping with phrases like uncertainty principle and observer effect. He hated it, not because it didn't work, it worked too well, but because it lacked clarity and worse, it seemed to imply that the universe didn't exist until someone looked at it. He believed the moon was there whether or not anyone was watching. You tend to agree, mostly because moons are terrifying enough without also being insecure. So he teamed up with Boris Podolsky and Nathan Rosen to publish the now famous EPR paper, laying out what they thought was a fatal flaw in quantum mechanics. The gist of it: if quantum theory says two entangled particles can instantaneously affect each other over large distances, then either A, the theory is incomplete, or B, it allows for faster-than-light influence. Einstein and his co-authors leaned hard into option A. They proposed that there had to be something missing, some hidden variable that would restore order and predictability. To them, quantum mechanics was like a puzzle box missing the final piece, elegant on the outside but hollow within. The EPR argument wasn't just an academic footnote. It sparked decades of fierce debate. You imagine rooms full of chain-smoking physicists arguing about whether the wave function is real or just a useful trick. Einstein believed in locality, that what happens here cannot instantly affect what happens over there. He also believed in realism, the idea that physical properties have definite values, regardless of whether they are measured. Quantum mechanics spat on both of those principles and did a little dance. The weirdest part: the EPR paper wasn't disproving quantum mechanics, it was challenging its completeness. They weren't saying quantum mechanics was wrong, they were saying it couldn't be the full story. Like looking at a shadow and insisting the object casting it must be more complicated than it seems. And for a while, many people agreed. After all, no one had proven that particles weren't carrying secret instructions from the moment they were entangled. That was a plausible escape hatch. Maybe the universe wasn't spooky, just subtle. But there was a catch. Quantum mechanics made predictions about correlations between entangled particles that couldn't be explained by any local hidden variables. It wasn't just a philosophical disagreement. It was a bet, and eventually someone would have to call it. But in the 1930s and 40s, no one had the tools to do it. The technology to test the predictions simply didn't exist yet. So the question sat there, brooding in the corner, like a cat who saw you move the treat jar, and now questions your entire character. Einstein passed away in 1955, never satisfied with the quantum explanations. He died believing that something better would replace the current theory. He trusted that a more complete understanding would eventually reveal a harmonious, non-spooky universe. But physics had other plans. One fringe story from that era that you might enjoy, if only for its late-night energy, involves an early advocate of quantum mysticism who suggested that entanglement might explain telepathy. Yes, actual mind reading. In the 1940s, some pseudoscientific circles flirted with the idea that if particles could be entangled across space, maybe human minds, too, were subtly linked. It never gained traction in the mainstream, obviously, but the notion stuck around, like a stubborn burr clinging to the wool sweater of serious science. And honestly, it's the kind of thing you wonder about at 2:47 a.m. after falling down one too many rabbit holes. As you lie there in the soft dark, you realize that Einstein's frustration wasn't rooted in denial. It was rooted in love, for logic, for clarity, for the dream that the universe is knowable. His rejection of entanglement wasn't just curmudgeonly, it was deeply principled. To him, allowing instantaneous effects across space meant giving up on the idea of cause and effect itself. And that, frankly, is a terrifying trade. It's like replacing the laws of physics with jazz improv and calling it a theory. Yet despite his protests, quantum theory marched on, gaining more and more predictive power. It worked. It explained experiments, predicted new phenomena, and eventually gave rise to technologies like lasers, transistors, and GPS. The very device you're listening to this on, a child of quantum mechanics. It turns out the universe doesn't care whether its rules make sense to us. It just keeps functioning silently, spookily, beautifully. Still, the ghost of Einstein's skepticism lingers. Historians still argue whether he ever truly got quantum mechanics or simply tolerated it as a useful evil. Some claim he misunderstood the theory's subtlety, while others say he was playing a deeper game, challenging physicists to think beyond what the math told them. Either way, his doubts planted seeds that would take decades to bloom. And bloom they did. Soon, a new generation of physicists would rise, one in particular, who would finally put Einstein's discomfort to the test. But before we meet him, you sit for a moment with the eerie possibility that maybe, just maybe, the universe isn't local, that everything really is connected, not by light or gravity or force, but by something deeper, something spooky. You wake into the dream again, back in that smoky lecture hall, chalk dust swirling through sunlight, equations hanging midair like spells, and there at the front stands John Stuart Bell. He doesn't look like a revolutionary. Neatly dressed, gentle voice, a soft northern Irish lilt, but the calm hides the storm. Because in the 1960s, Bell finally cracked open the safe Einstein had been pounding on for decades. He didn't break the lock, he picked it. Quietly. Brilliantly. With what would become one of the most important results in modern physics, Bell's theorem. You settle deeper into your blanket because Bell's idea isn't just clever, it's seismic. Up until then, physicists who disliked quantum weirdness still had a way out. They believed hidden variables, tiny, undetectable properties baked into particles, could explain the spooky behavior. In their minds, entangled particles weren't communicating faster than light. They were just revealing information they already had, like opening two matching envelopes that were stuffed ahead of time. Predictable, sensible, comfortably classical. But Bell wasn't convinced. He thought, if there really are hidden variables controlling outcomes, then those variables must obey certain limits. He crafted a thought experiment, a mathematical inequality that said, in effect, if the universe plays fair with local realism, then the correlations between entangled particles can only be this strong. But quantum mechanics predicted stronger correlations, just enough to tip over that line. So if experiments ever broke Bell's inequality, local realism had to go. You couldn't keep both. Either the universe is local or it's real. Not both. Choose your poison. That's the genius of it. Bell didn't just complain about quantum theory. He offered a way to test it, a way to move the fight from smoky debates into cold, hard labs. And once the physicists had something they could actually measure, things got wild. Experiments started in earnest in the 1970s, most notably by Alain Aspect in France. You imagine him, lab coat, sleepless eyes, firing entangled photons through beam splitters and detectors, trying to see if the numbers matched Bell's expectations or quantum mechanics. Spoiler, they matched the quantum side. Again and again, experimenters found that entangled particles show correlations stronger than any local hidden variable model allows. It's like guessing the same coin flip result as your friend 20 times in a row, even though neither of you can see each other, talk, or cheat. Eventually, the odds stop looking like coincidence. They start looking like something deeper is linking your choices, something faster than light, something that doesn't care about distance or even the idea of space at all. But wait, there's a sleepy catch. Bell's theorem doesn't prove faster than light communication. It proves that no theory based on local hidden variables can reproduce the predictions of quantum mechanics. The math says, if you believe in locality and realism, your prediction should cap at X, but the universe hits X plus 1. That's enough to throw classical assumptions out the window, but it doesn't exactly tell you what's happening instead. It just tightens the noose. Fringe detail incoming. For years, skeptics poked at possible loopholes in these experiments. Maybe the detectors weren't efficient enough. Maybe the particles were influenced by something before the measurement. Or maybe the choice of what to measure wasn't truly random. One particularly odd idea, the freedom of choice loophole, suggested that the universe could be subtly conspiring to align everything just right. As in, the particle's properties and the experimenter's decisions were predetermined by something unknown. Free will, optional apparently. Bell himself acknowledged these loopholes but remained confident. He believed that eventually experiments would shut them down, and over time they did. Each new trial patched a different hole in the logic: better detectors, more randomness, greater distances. In 2015, the loophole-free Bell test was finally achieved by researchers in the Netherlands, our sleepy friends in Delft who will visit again soon. Their results confirmed the quantum predictions. Local realism. Declared officially untenable. And here, where things get dizzying, Bell's theorem is not just about entanglement, it's about the nature of reality itself. If entangled particles can't be explained by local hidden variables, then either locality is dead, or reality doesn't exist in the way we think. Maybe measurement doesn't reveal a value, it creates one. Maybe space isn't what separates things. Maybe cause and effect are just convenient illusions. Historians still argue whether Bell fully understood the implications of his own theorem, or whether he was merely showing that something had to give. But the result is clear. There's no going back to the cozy world of classical physics. The door is shut. The bridge is burned. The ghost of Einstein still paces the hallway, but he can't unring this bell. One lovely quirk: Bell was a philosopher at heart. While many physicists ignored the interpretation of quantum mechanics in favor of practical results, Bell wanted to understand why. He wasn't content with equations that worked. He wanted meaning. He thought deeply about what entanglement meant for determinism, for the fabric of the universe, even for consciousness. Late in his life, he expressed doubts about the Copenhagen interpretation, that weird idea that particles don't have definite properties until we observe them. He called it unprofessionally vague and ambiguous. You feel that in your bones. So you lie here now, caught between two impossibilities. Either the universe is non-local, meaning effects can happen across space instantly, or reality itself is conditional and blurry until observed. Either way, something you thought was fundamental isn't. And while you ponder that, two entangled photons continue spinning in opposite directions, whispering to each other across the dark, faster than light, or maybe outside time altogether. Bell didn't solve the mystery. He just proved there's no hiding from it anymore. You're drifting now, slower and softer, into a small Dutch lab on a quiet night in 2015. Outside, bicycles lean silently against brick walls and street lamps glow with sleepy orange halos. Inside, though, the air buzzes with anticipation. In the town of Delft, two teams of physicists are about to pull off something Einstein would have hated and Bell would have loved: a loophole-free test of entanglement. Not a thought experiment, not a simulation. A real-world showdown between quantum mechanics and the last remaining refuge of classical physics. You nestle into the folds of your blanket. This is the moment we stop arguing and start measuring. The experiment is delicate, bordering on absurd. Two labs housed in different buildings sit 1.3 kilometers apart, just enough distance that any information traveling at light speed wouldn't have time to cheat the results. Inside each lab, a single electron is trapped in a diamond. Yes, literal diamonds, using lasers and magnetic fields. These electrons are then entangled with individual photons, which race across the distance between the labs to a central station. If those photons successfully swap their entanglement, then the electrons, still sitting quietly in their separate buildings, are now entangled with each other. Let that sink in. The two electrons have never touched, never shared a space. They weren't even born at the same time. But thanks to the magic of quantum entanglement and clever lab work, they're now bound by a connection so deep that measuring one will affect the other. This isn't theoretical anymore. This is your bedtime story becoming a physics paper. The experimenters go further. To rule out the last stubborn loophole, they randomize the measurement settings after the entanglement is established. They use two independent random number generators, fast enough that the choice of what to measure can't possibly influence or be influenced by the other side. No advanced warning, no chance for the particles to collude. The measurements are made, the data is recorded, and then the result, Bell's inequality, is violated. Again, decisively. What does this mean? It means entanglement isn't some lab artifact or trick of bad measurement. It means the spooky action is real. It means the universe, when tested under the strictest conditions humans can muster, behaves in a way that no local, classical theory can explain. You almost feel the ground shift beneath you. Not because it's a surprise, it was predicted decades ago, but because now there's no running from it. The results are too clean, too repeatable, too consistent. And yet, it's still not faster than light communication. That's the part that trips you up every time. You feel like if one particle affects another instantly across kilometers, surely that must mean information is being transferred faster than light. But the trick is in the word information. You can't control what the particle reveals when you measure it. It's still random. The instant link only shows itself when you compare notes later. Until then, all you have is noise. Spooky correlated noise, sure, but noise all the same. Still, the implications keep echoing. These experiments don't just reinforce quantum theory, they demolish any lingering hope of a return to classical explanations. There are no hidden variables that explain everything neatly. No pre-written script that the particles are following. Either space isn't real in the way we think, or reality isn't local. Pick your existential crisis. A quirky side note from the Delft lab. The experiment required such low error rates and such precise synchronization that they actually had to pause between measurements to let everything cool down. Imagine entangled particles waiting politely for the lab equipment to catch its breath. Even quantum weirdness needs a coffee break. Historians still argue whether this experiment marked the end of the Einsteinian dream for good. Some say it closed the book on local realism. Others insist there are still philosophical questions open, about interpretation, about determinism, about what measurement really means. After all, quantum mechanics gives you the right answers, but it doesn't tell you what's actually happening behind the curtain. The math says, you'll get result A or B, but doesn't explain how the system chooses. It's like getting your fortune read and realizing the universe has no interest in explaining itself. You find that unsettling, but also a little poetic. Here we are, these soft, sleepy creatures lying under blankets, trying to understand a universe that doesn't seem to care whether it's understandable. And yet we measure, we question. We trap electrons in diamonds and whisper across the void with photons. And maybe, just maybe, that's the real magic. Not the entanglement itself, but the fact that we can witness it. That we can build delicate machines in sleepy towns and capture something that stretches the limits of space and time. That, even in the middle of a cold Dutch night, surrounded by blinking equipment and humming wires, we can glimpse a truth so strange it defies common sense. So you close your eyes and imagine those electrons, still sitting in their diamond prisons, forever entangled, forever waiting. No wires, no signals, just a bond so perfect it doesn't need space. You wonder if the universe is like that too, a vast web of entanglements we'll never fully see, but sometimes just briefly feel. You're floating now in that strange mental in-between, where science becomes a lullaby and the laws of physics feel more like poetry than equations. And yet, as the haze of quantum slowly clears, a stubborn little question drifts up from the void like a balloon. If entangled particles affect each other instantaneously, doesn't that mean they're somehow communicating faster than light? The answer, like most things in quantum physics, is a frustrating yes and no, which is either comforting or infuriating, depending on how much sleep you've had. To understand what's going on, you'll need to tiptoe right up to the edge of what Einstein held sacred, the universal speed limit. According to special relativity, nothing can travel faster than the speed of light. Not information, not matter, not energy, not even a desperate email to your advisor at 11:59 p.m., and that rule is rock solid. You can stretch space, warp time, even approach the speed of light, but you can't break it. Unless, apparently, you're an entangled particle. Because whatever this weird connection is, it seems to happen instantly, zero delay. One particle knows what happened to its twin, no matter how far away. So why doesn't this violate relativity? Here's the sleepy loophole. Entanglement does create correlations faster than light could travel, but you can't use those correlations to send actual messages. The results of measuring each particle are random, completely unpredictable. It's only when you compare the data after the fact, using good old-fashioned light-speed communication, that the spooky pattern emerges. It's like two magicians flipping cards in different cities and always getting matching suits. But neither of them knows what they're going to flip next. The magic is in the pattern, not in any message being sent. The technical term here is no signaling theorem, and it's baked right into the math. Quantum mechanics stubbornly refuses to allow faster-than-light communication, even if it flaunts everything else. The entanglement correlation is instantaneous, but the data remains stubbornly mute until both sides are brought together and compared, which is either brilliant design or a cosmic prank. You wonder, is the universe just teasing us, giving us this mysterious, elegant phenomenon that looks like faster-than-light influence, but always slipping just out of reach when we try to use it for anything useful? You imagine some cosmic trickster particle leaning on the table, whispering, "Sure, we're entangled. Sure, we coordinate instantly, but good luck using that to call your grandma." Still, the question lingers. If something changes there the moment you do something here, then some kind of influence must be traveling between them, right? And if it's happening faster than light, even without carrying information, what is it? That's where things get murky. Some physicists say it's just non-locality, no need for any influence or signal, just a reality that isn't bound by space the way we think. Others propose superdeterminism, which suggests that everything, your measurement choices, the particle outcomes, even your decision to listen to this podcast, is predetermined. No free will, no randomness. Just one giant clockwork universe where everything clicks into place. That's not exactly a comforting bedtime thought, so let's turn the lights down a bit more. One fringe notion, whispered in the physics back alleys, is that entanglement might represent a kind of quantum information channel that exists outside spacetime. Not through spacetime, outside it. Imagine space and time as a fuzzy stage, and entanglement as actors whispering cues from behind the curtain. You don't see the communication, but you know something going on. The big problem is, no one knows what the curtain is made of. Quantum field theory doesn't offer a clear picture of where or how entanglement exists. It just works, like a TV remote that still functions even after you've taken the batteries out. Convenient, but unnerving. Historians still argue whether this loophole-free but still no signaling setup is a satisfying answer or just a cleverly disguised contradiction. Some say it's proof that our current frameworks, quantum mechanics and relativity, are incomplete, like two puzzle pieces from different boxes that only kind of fit if you squint. Others argue that the tension is precisely what makes the universe interesting, a sort of creative discomfort embedded in the code of reality. There's even a term for this fuzzy quantum connection, quantum non-locality. It doesn't imply faster-than-light travel. It implies that the very concept of distance may not be fundamental at all. If two particles can influence each other without regard to distance, then maybe space isn't the backdrop we think it is. Maybe it's an emergent property, a side effect of something deeper, like the surface of the water in a lake, smooth, continuous, rippling, but underneath, molecules moving in wild, chaotic ways we can't see. It's a dizzying thought, so you anchor yourself with something more solid, the fact that all the experiments agree. From the early Bell tests to the modern satellite-based quantum experiments in China, everything lines up with quantum theory. The spooky action is real. It just doesn't let you cheat. You can't send a text message to Andromeda using entangled qubits, no matter how many YouTube videos claim otherwise. One particularly quirky idea from the mid-2000s suggested that entanglement might allow faster-than-light influences if you sacrificed causality. As in, the effect happens before the cause. Wild, right? But even then, when the math is pushed to its limits, the outcome is the same. No signal, no message. The universe teases, but it doesn't bend. So you're left with this beautiful tension. Entanglement is faster than light, but also not. It breaks our intuitions, but not our laws. It's the universe doing interpretive dance while insisting it's a rigid ballet. You lie there, eyes heavy, imagining a web of entangled particles stretching across the galaxy, softly pulsing, each tug on the thread felt instantly by the rest. No noise, no messages, just connection. And somehow that's enough. You lie motionless now, listening to the faint hum of your thoughts. The questions still buzz, quietly, persistently, as you drift deeper into the hazy realm of quantum interpretation. You followed entangled particles as they danced across continents and conspired faster than light. But there's one thing you haven't quite understood yet. What actually happens during a quantum measurement? That's the real rabbit hole, the one physicists have been tumbling down for over a century. Because entanglement is weird, sure, but the idea that a particle exists in a blurry, undefined state until you look at it, that's where things truly go sideways. This strange idea is tied up in something you've heard whispered before, the wave function. In quantum mechanics, particles aren't described by simple properties like position or velocity. They're described by a wave function, a sort of mathematical ghost that encodes all possible outcomes at once. Until you measure the system, it doesn't choose a reality. It just floats, ambiguous, like a coin spinning forever in midair, never landing on heads or tails. Schrödinger hated it so much he imagined a cat locked in a box, half dead, half alive, just to illustrate how ridiculous it all sounded. And here, where things get twisty, the act of measurement, of observing the particle, is what collapses the wave function into a single, definite outcome. Before that, your photon or electron isn't spinning up or down, it's spinning in a blend of both. Only when you interact with it does it decide what to be. This is called wave function collapse, and it's not just spooky, it's philosophical dynamite. Because suddenly, the observer, the you lying there under your blanket, becomes part of the equation. You're no longer outside the system looking in. You're tangled up in it, entangled even. The Copenhagen interpretation, the one most physicists grew up on, leans hard into this. It says, don't ask what the particle was doing before you measured it. That question is meaningless. The only thing that matters is what you observe. Reality doesn't exist in a definite form until it's measured, which is a polite way of saying, mind your business and trust the math. But not everyone buys that. You might be surprised to learn that even today, scientists argue bitterly, quietly but bitterly, over whether wave function collapse is a real physical event or just a trick of incomplete knowledge. Some interpretations, like the many worlds theory we'll whisper about soon, say the wave function never collapses at all. Instead, every possible outcome does happen, just in different universes. Somewhere you measured spin up, somewhere else spin down, and somewhere in between, your brain quietly exploded from the implications. Back in the 1960s, a physicist named Hugh Everett proposed this many worlds view, hoping to preserve the purity of quantum math without the pesky problem of collapse. But other camps formed too. The decoherence camp, for instance, argues that measurement isn't magic. It's just the result of a quantum system interacting with its environment, like a whisper getting drowned out in a stadium. The system's possibilities blur into the background noise until only one reality seems to emerge. No collapse, no drama, just math smoothing itself out. There's even a dreamy fringe theory called objective collapse, which suggests that wave functions collapse randomly, independent of observers when a certain threshold is reached. In this view, reality really does make up its mind at some point, no human required. It's like the universe flipping a coin and deciding, all right, enough ambiguity. Let's go with this one. The most famous version of this, the Rimini-Weber GRW theory, introduces spontaneous collapses at random intervals. It's messy, but it saves you from having to ask whether your consciousness is quantum code. And yet we still don't know. Historians still argue whether the concept of wave function collapse even makes sense, or whether it's a sign that quantum theory, while insanely accurate, isn't the whole story. After all, you can't see a wave function. You can't poke it or bottle it or send it through customs. It's an abstract tool that tells you probabilities, nothing more. So maybe, some say, the collapse is just you catching up with the universe, not the universe changing in response to you. Here's a quirky little tidbit to chew on. In 1978, a physicist named Eugene Wigner actually proposed that human consciousness itself might be what causes the wave function to collapse. That it's your awareness, your act of knowing, that resolves quantum ambiguity into a concrete outcome. He later backed away from the idea, but not before launching 1,000 late-night dorm room conversations and at least 3 psychedelic rock albums. The idea never really died. It just joined the long list of interpretations physicists love to argue about at conferences between coffee breaks. So where does that leave your entangled particles? If measurement collapses the wave function, and if 2 particles are entangled, then measuring one collapses both instantly. This fits neatly with what experiments show. But what it means, philosophically, ontologically, cosmically, is a tangled mess. Is the second particle's state determined at the same moment as the first? Or was it already secretly fixed all along? Does the collapse travel? Does it need to travel? Or are we just asking the wrong questions altogether? You roll over slowly, the questions flickering like dim stars in the dark. Every answer quantum mechanics gives is cloaked in probability and framed in paradox. It's a theory that works perfectly but explains almost nothing. Or perhaps it explains everything, and we're the ones who aren't ready to understand it. You imagine a wave function now, rippling across the cosmos, not a thing but a cloud of all things. Infinite futures, infinite pasts, until suddenly collapse, decision. One path, one spin, one cat alive or dead. One sleepy listener wrapped in a blanket wondering what it all means. Maybe it means nothing, or maybe it means the act of wondering is itself part of the equation. That without you asking the question, there's no answer at all. You're drifting now in a slow orbit around one persistent question. If entangled particles seem to influence each other instantly, why can't we use that connection to send messages faster than light? You picture it, two people, each with half of an entangled pair, sitting on opposite sides of the galaxy. One flips a switch, the other sees it instantly. Telepathy, warp-speed communication, the end of long-distance charges. And yet, it doesn't work. No matter how perfectly entangled your particles are, no matter how carefully you prepare your experiment, you can't use entanglement to send usable information. The quantum universe is generous with weirdness, stingy with shortcuts. This is the heartbreak of entanglement. The connection is real, but it's also mute. Yes, measuring one particle affects the other, but not in a way you can control. When you measure your particle's spin or polarization, you get a result, up or down, left or right. It's random, totally unpredictable. The spooky part is that your partner, miles or light years away, will get a correlated result, but they'll also see random data. It's only when you compare results later, at regular old subliminal speeds, that the pattern emerges. The entanglement is undeniable, but the message is locked behind probability. This limitation is formalized in the no-communication theorem. It tells you that quantum mechanics, for all its spooky action, is meticulously careful about preserving causality. You can't use entanglement to send a message faster than light because any individual outcome looks like noise. It's only in the joint statistics that the magic reveals itself. So your dream of building a quantum texting service from Earth to Mars, crushed. You can't send "I love you" through entangled photons. Not unless you're okay with a 12-minute delay and a lot of garbled guesswork. Still, that hasn't stopped people from trying. In the 1990s, a few eager minds proposed protocols they thought might sneak a message through using clever measurement tricks. Some involved entangling 3 or more particles. Hopping the complexity would let one person nudge the odds in their favor. Others imagined using wave function collapse as a signaling device. But every scheme eventually crashed into the same wall. Quantum mechanics doesn't allow you to choose the outcome of a measurement. And if you can't choose the message, you can't transmit one. You might ask, what if you measure your particle in a specific way? Can't that influence what your partner sees? But the problem is, they can't tell which way you measured. Their results remain perfectly random. The only thing that changes is how the two sets of measurements correlate. It's like each person watching a scrambled movie, and only when they overlay their tapes do the images snap into focus. Here's a fun analogy. Imagine you and your friend each get a pair of dice. The dice are enchanted, entangled. When you roll yours, your friend's die will always land on a number that matches a pre-agreed pattern, but only if they rolled it at the same time, using the same method, and only if you both compare results later. Otherwise, just two boring six-siders. Roll, stare, shrug. There's a quirky historical detail here, too. In the 1980s, a physicist named Nick Herbert proposed a device called the quantum no-cloner, which he believed could use entangled particles to send messages instantly. His plan hinged on copying quantum states without destroying them. But that idea collided head-on with the no-cloning theorem, which says you can't make a perfect copy of an unknown quantum state. Not even one. The universe just doesn't allow it. As a result, Herbert's proposal was refuted, but not before it inspired a wave of deeper investigation into quantum information theory. So even bad ideas sometimes give birth to good science. And what about those wild theories that entanglement could explain telepathy, or that alien spacecraft might use it to communicate across the stars? Those ideas sound cool at 3 a.m., but they don't hold up to daylight. You can't use entanglement to send intent. You can't use it to pass codes. You can't, as far as the math says, use it to do anything besides freak yourself out and win Nobel Prizes. Historians still argue whether Einstein's real issue with quantum mechanics was the randomness, the non-locality, or the maddening combination of both. But what remains clear is that even he couldn't find a loophole to exploit for communication. Spooky action, sure. Useful spooky action, not so much. So does this mean entanglement is useless? Far from it. The inability to send messages doesn't make entanglement less real, it just makes it less convenient. In fact, the very impossibility of faster-than-light messaging is what makes quantum cryptography so powerful. We'll touch on that in a bit, but here's the gist. Because no one can intercept an entangled connection and extract information without disturbing it, entanglement becomes the perfect lock. You can't break into it. You can't spoof it. The act of trying ruins the result. It's a strange twist of nature's logic. What you can't use for signal, you can use for secrecy. Still, you can't help but imagine what it would be like if the rule wasn't there. If entanglement really did let you bypass the speed of light, interstellar calls, emergency messages from distant colonies, real-time chats with Voyager 1. But the universe says no, again and again in every experiment. The spooky link is real, but it respects the cosmic speed limit. Or maybe, just maybe, the limit isn't about speed at all. Maybe it's about what information even means. You blink slowly, the quiet weight of that thought settling over you like a soft quilt. In quantum physics, information isn't a whisper carried on the wind. It's a deep structure, encoded in probabilities and measurement choices. It's a pattern you can't see until you stop trying to force it. And entanglement, that's just one way the pattern tells you it's there. So for now, you'll have to settle for your usual signal lag, your light-speed news feeds, your good old-fashioned wireless connections. Entanglement will stay in the background, watching, synchronizing, but saying nothing. And perhaps that silence is its message. So here you are, wrapped in the dark, staring at the ceiling, thinking about teleportation. And no, not the Star Trek kind where you step onto a glowing platform and your atoms get beamed across the galaxy while you somehow keep your hair cut. Real quantum teleportation is weirder, slower, and somehow more elegant. You don't move particles from one place to another. Instead, you transmit their exact quantum state, using entanglement as a bridge. It's like destroying the original copy of a document and recreating an identical version somewhere else without ever printing it. You don't move the thing, you move the being of the thing. It starts, as always, with entanglement. Imagine two people, let's call them Alice and Bob because physicists are secretly fond of simplicity, each holding one half of an entangled pair. Alice also has another particle, one she wants to teleport to Bob. She doesn't want to send the particle itself, just its quantum state, the delicate, precise way it's spinning, oscillating, and existing in a haze of possibilities. But she can't just read that information and email it over. Remember the quantum rulebook. If you try to measure the state directly, it collapses, and all the juicy details get ruined. So instead, she uses a strange workaround. She performs a joint measurement on her particle and her half of the entangled pair, a specific type of measurement called a Bell state measurement. This action causes the state of her particle to be transferred to Bob's distant one. Not copied, but transferred. Bob's particle, which up until now was just sitting there all chill and quantum, is now an exact replica of Alice's original particle. Not in looks, not in matter, but in quantum state. It behaves as if it is Alice's particle. And yes, this process destroys the original state in the process. The original is gone. Only the copy survives. Teleportation complete. You might ask, okay, but did that happen instantly? Did Bob's particle change the moment Alice did her measurement? And in a spooky yes but no way, yes. But he can't use that information until Alice sends him some extra classical data. That's the kicker. In order to reconstruct the original state on Bob's end, Alice must send him two classical bits of information: what measurement result she got. Only when he receives that message can he apply the correct transformation to his particle and make it behave like the original. Until then, Bob's particle just sits there, unresolved, suspenseful but silent. So despite the teleportation metaphor, this process doesn't allow for faster-than-light transfer of usable information. That classical message from Alice to Bob still has to obey the light speed limit. But the entanglement itself makes the whole thing possible. Without it, the state would be lost forever. Still, it's kind of beautiful, isn't it? The idea that something so fundamental, so it can be disassembled here and rebuilt over there perfectly, as if distance didn't matter. It makes you wonder what place even means when a particle's state can slip across space without traveling. And yes, scientists have done this in real life. In fact, they've teleported quantum states between particles in labs, across fiber optic cables, and even from Earth to space. In 2017, Chinese researchers successfully performed quantum teleportation of photon states between the ground and a satellite orbiting more than 500 kilometers above. They didn't send a particle to orbit. They sent the particle's essence, carried by entanglement and confirmed by delayed classical signals. It wasn't instantaneous magic, but it was a first step toward building quantum communication networks. That's right, quantum internet is on the menu, though the service will probably still drop during thunderstorms. There's a fringe twist, too. Some people, not mainstream physicists but persistent thinkers on the edges, have proposed that teleportation might one day extend to more complex systems, like molecules, or memories, or you. Now, before you try to print a boarding pass to Saturn, keep in mind, we're nowhere near being able to teleport anything remotely as complicated as a human brain. The amount of information involved is astronomical. Not to mention the tiny problem that you'd need to destroy the original you to reconstruct the quantum state elsewhere. Small hiccup, slightly existential. Still, the idea has power. It challenges your sense of self, of space, of what it means to exist in a place. If your quantum state can be transferred, are you what moves, or just your pattern? Is there a meaningful difference? These are the kinds of thoughts that keep theoretical physicists awake and the rest of us softly panicking at midnight. Historians still argue whether quantum teleportation represents a fundamentally new kind of communication or just a clever extension of existing principles. Some say it shows us how deeply entanglement can be harnessed to move information. Others believe it's a technological trick, nothing more than math and lasers and well-timed measurements. But no one denies that it works. We've tested it. We've watched it. The teleportation isn't metaphorical. It's literal, within the confines of quantum logic. And here's the part that truly messes with your dreams. The process of teleportation is irreversible. Once the original state is transferred, it's gone from where it started. The universe updates itself. There's no duplicate, no backup, no quantum carbon copy. It's a one-way street, which sounds hauntingly poetic when you think about it. Every teleportation is a little death and rebirth. So tonight, as you lie there tangled in sheets and quantum metaphors, you imagine yourself entangled with someone far away. You imagine whispering not words but states, being not in one place but across many. You picture yourself measured, collapsed, and reconstructed, not as atoms but as pattern, possibility, wave function. Not gone, just moved. Teleportation isn't about moving particles. It's about rearranging reality. And somehow, you're already a part of it. You're drifting deeper now, and as the hum of quantum strangeness grows familiar, your thoughts settle on time. Not just the ticking clock kind, but the deep, weird kind. The time that bends, slips, reverses, or gets completely ignored by entangled particles. Because if space doesn't matter to them, what about time? If two particles can influence each other faster than light, are they also skipping across seconds, brushing past causality and giggling behind relativity's back? The more you think about it, the more slippery everything becomes. And that's exactly where the quantum story gets even weirder. Let's say you entangle two particles and send them off in opposite directions. Easy enough, done all the time in labs. Now imagine that you delay your measurement on one side. Let the first particle get measured now, but the second one. You don't touch it until later, much later. According to the math, it doesn't matter. Measure one now, measure the other next year. The outcome remains entangled, and not just statistically. The measurement you perform now still affects the result of the other particle, even if that measurement technically happens after the other one was already measured in its reference frame. Welcome to relativity's headache. This is called the relativity of simultaneity, and it's a concept straight from Einstein's own playbook. What looks like now to one observer can look like later or earlier to someone moving at a different speed. So when two entangled particles are measured in different locations, there's no universal agreement about which measurement came first. It depends on who's looking from where and how fast they're moving. The entire idea of before and after starts to dissolve, especially in a quantum context. So what does this mean? Can the future influence the past? Can your decision to measure something now affect the outcome of something that's already happened from someone else's point of view? It's not just theoretical, it's been tested. In so-called delayed choice experiments, physicists have shown that entangled particles behave as if they know how they'll be measured, even if that choice is made after one of them has already hit a detector. Somehow, the system adjusts to preserve entanglement correlations across time. You shift uneasily because this starts to sound like science fiction, but it's real. Delayed choice quantum eraser experiments, pioneered in the late 20th century and performed again and again in various labs, show that entangled particles retain an eerie awareness of measurement decisions, even if those decisions happen after the particles are gone. In one setup, a photon goes through a double-slit apparatus and forms an interference pattern, classic wave behavior. But whether or not the interference appears depends on a measurement made on its entangled partner after the first photon has already hit a screen. Somehow, the past seems to rewrite itself based on a future choice. Now, does this mean time travel is real? Not quite. You can't send messages backward through time. You can't warn your past self not to eat that gas station sushi. What it does mean is that quantum events don't seem to respect the tidy timeline we experience. In the quantum world, time flows less like an arrow and more like a puddle, wobbling, sloshing, responding to measurement more than marching forward. Historians still argue whether this means causality itself is broken, or if we just need better language for what's happening. Some physicists believe the universe doesn't have a single, fixed sequence of events. Instead, what counts as cause and effect might emerge from more fundamental quantum rules. Others propose that time is an illusion altogether, a psychological artifact, not a physical law, but nobody agrees, not even close. Here's a fringe tidbit that might make you sit up in bed. In 2009, a pair of researchers proposed something called the two-time interpretation of quantum mechanics. In this model, events are determined not just by conditions in the past, but also by conditions in the future. A measurement result is the result of boundary conditions from both directions in time. It's like a tennis match played from both ends of the court simultaneously, with the ball somehow obeying both players. The math works, the idea still deeply controversial. So what about entangled particles experiencing time differently? Imagine one twin particle zipping away near the speed of light while the other stays close to home. Thanks to time dilation, a confirmed prediction of relativity. The fast-moving particle ages more slowly. This isn't science fiction. GPS satellites literally have to account for time dilation due to both velocity and gravity. But if these two particles are entangled, does the slowing down of one's clock affect the way their shared state evolves? Can one be older in entangled time? We don't have a perfect answer yet. Quantum entanglement and relativity don't always play nicely together in the math, but some experiments suggest that entanglement persists even when particles are accelerated or put through different gravitational fields. In one proposed experiment, physicists aim to test entanglement with one particle on Earth and another on a spacecraft moving at high speed. If the entanglement holds despite the time difference, it would imply that quantum information exists outside the normal constraints of time. And that's what keeps physicists, and maybe you, lying awake at night. Entanglement doesn't just challenge space, it shakes the very foundation of time. It hints that our clean little sequence of moments, first this, then that, may not be how the universe actually runs. What feels like causality might be something emergent, soft, or negotiable. So you stare at the ceiling now and time stretches. Past, present, future. Each thought slides into the next, the way entangled particles seem to blur position and momentum, identity and role. You think about all the times you've made choices you couldn't explain, decisions that felt inevitable. And you wonder softly if those moments were connected to others, not just across distance but across time. Maybe the universe remembers forward and backward. Maybe it doesn't remember at all. But somewhere, two photons born in the same spark still whisper, still spin, still keep time with each other in a rhythm we don't yet understand. And somehow, that feels like a kind of peace. The deeper you sink into the quiet, the more it becomes clear that causality, the simple idea that one thing leads to another, isn't as rock solid as you were led to believe. In your everyday world, you pour water into a glass and then the glass fills. You say something and someone answers. There's a rhythm, a direction. But in the quantum world, entanglement smirks at all that. It forces you to ask, which event actually causes the other? Does your act of measuring a particle determine its state? Or does the outcome already exist, waiting for you to catch up? Let's stretch that thought. Suppose two entangled particles are flying in opposite directions. You measure one, and instantly the state of the other becomes known. But why do you assume your measurement caused that change? What if the state of the distant particle had always been that way, and your observation just confirmed it? But if that's true, then you're back in the realm of hidden variables, the very thing Bell's theorem already ruled out. So if you didn't just reveal an existing property, and if the measurement does influence the distant particle, then you've got a causality problem on your hands. But here's the kicker. The problem goes both ways. There's no universal clock in the universe. Thanks to relativity, what you consider now isn't the same for someone zipping past at near light speed. From their perspective, the second measurement might happen before the first. So which measurement is the cause and which is the effect? The answer, unhelpfully, might be neither, or maybe both. Or maybe causality is just a thing our brains invented to feel sane. This confusion is at the heart of what physicists call the quantum causality crisis. In classical physics, every effect has a cause, and those causes happen in the past. Quantum mechanics throws a wrench into that by allowing correlations between events that defy any clear timeline. You can't always say which came first, and yet the outcomes are always connected. It's like reading 2 pages of a book in random order, but somehow the story still makes sense. One proposed escape hatch is to abandon the idea of a fixed causal order altogether. In 2012, researchers proposed a framework called process matrices, which describes scenarios where the order of events isn't well defined. In these quantum setups, it's not that one thing causes another, It's that the events are linked, but the direction of influence is fuzzy. You might measure your particle before your partner measures theirs, or after, or neither. It doesn't matter. The system only cares about the combined result. And yes, someone actually built this. In 2019, physicists demonstrated a causal non-separable process using photons, showing that in certain quantum situations, you can't tell whether event A causes B or B causes A. It's like an Escher staircase made of measurements. Everywhere you look, something's upstream and downstream at the same time. So what does this mean for entangled particles? It means their behavior doesn't require a classical cause-and-effect structure. One measurement doesn't trigger the other in the way a bowling ball knocks over pins. Instead, the outcomes arise from a shared quantum state, one that doesn't care about which happened first. The universe, in these moments, behaves less like a sequence of events and more like a song with harmonies you can't pull apart. There's a fringe theory, of course there is, that suggests causality itself is a quantum variable, that in some deeper theory, cause and effect might emerge from entanglement rather than the other way around. That idea turns everything upside down. Maybe particles aren't entangled because they were connected in the past. Maybe their connection creates a kind of past, a retroactively justified history, stitched together by the act of measurement. Historians still argue whether quantum causality can be reconciled with relativistic constraints. Some say we need a new theory of time, one where time isn't a line but a web. Others believe we're misinterpreting quantum mechanics entirely, and that causality is fine. It just looks weird from our limited vantage point. Either way, the crisis isn't resolved. It's more like a fog that deepens as the light gets brighter. But you don't need a degree to feel it. You just need to watch two entangled particles do their dance. You can flip a coin here and it lands heads. You check a coin on the other side of the galaxy and somehow it lands tails. Every time. Not because one flip caused the other, but because they're parts of the same coin. The same wave function, split in space but not in meaning. You roll onto your side now and the thought settles in like dust. Maybe you've misunderstood cause and effect your whole life. Maybe what looks like cause is just correlation with better PR. Maybe your choices aren't the first steps of consequences, but the echoes of something shared, something bigger. Like entangled particles spinning in silence, linked not by wires but by meaning. And if that's true, then maybe the comfort isn't in understanding, but in accepting that some things just happen together, without one making the other, without time to separate them, only the quiet fact that they are. The hum of thought quiets a little as you drift into something more grounded. After all this cosmic confusion, instantaneous influences, timelines collapsing on themselves, particles in quantum limbo, you're ready for something practical, something real, something that proves this isn't just a philosophical fever dream whispered by caffeinated physicists. So you open one eye and peer into the softly blinking world of quantum technology, where entanglement isn't just a curiosity, it's a tool. And it's already changing your world, whether you know it or not. First up, the crown jewel, quantum cryptography. Sounds intense, but here's the sleepy breakdown. In classical cryptography, when you want to send someone a secret message, say your Wi-Fi password or your obsession with a certain reality TV show, you use encryption keys. Those keys need to be exchanged securely. If someone intercepts them, game over. But quantum key distribution, QKD, particularly in protocols like BB84, uses entangled photons to generate and share encryption keys in a way that's fundamentally tamper-proof. Here's the spooky advantage. If a hacker tries to eavesdrop on the quantum key exchange, the mere act of observing the entangled photons collapses their state, immediately alerting the sender and receiver. It's not that you catch them red-handed, it's that the universe itself snitches. No alarms, no firewalls, just physics enforcing privacy. You can't clone entangled states. You can't intercept them unnoticed. The system breaks itself rather than let your secrets slip. And this isn't theory anymore. Quantum cryptography is already being deployed. Banks in Switzerland have tested it for secure communications between branches. In 2017, China launched the Michus satellite, named after an ancient Chinese philosopher who probably never imagined his legacy would include space lasers, to test satellite-based quantum key distribution. It worked. They transmitted entangled photons from orbit to Earth, proving that secure quantum communication is possible on a global scale. And yes, it's exactly as cool as it sounds. But the dream doesn't stop at privacy. There's another shimmering horizon on the edge of the sleepy quantum sea: quantum computing. These are machines that don't just use ones and zeros, but qubits, quantum bits that can be in superpositions, entangled and manipulated in ways no classical computer can match. With enough entangled qubits, a quantum computer can perform certain calculations exponentially faster than anything your laptop could hope to achieve, even if it drank 4 energy drinks and a thermos of ambition. One of the most mind-bending properties of quantum computing is the way entanglement allows for parallelism. A system of entangled qubits doesn't just compute one outcome at a time. It explores many possible outcomes simultaneously. It's like having millions of ghost computers running in parallel, all tied to one real result. And when the measurement comes, the right answer collapses into view. Creepy, powerful, and deeply elegant. As of now, we're still early in the game. Companies like IBM, Google, and startups you've never heard of are building quantum processors that use trapped ions, superconducting loops, and even photons to hold and manipulate qubits. Most current machines operate with just a few dozen usable qubits, delicate, error-prone, and easily spooked by environmental noise. But the race is on to scale up. If it works, we could simulate molecules with precision that makes today's chemistry look like drawing atoms with crayons. And yes, that might mean a quantum computer will eventually simulate your brain. But let's not worry about that right now. Now for the obligatory quirky fringe detail. In 2013, a group of researchers in Australia claimed to have created a quantum cat using superconducting circuits, a system that behaved both like a classical cat and a quantum one, depending on how you looked. It wasn't fuzzy, didn't purr, and never sat on your keyboard, but it showed superposition-like behavior in a macroscopic system. A Schrödinger's cat homage, but with more wiring. Of course, we'd be irresponsible not to mention quantum metrology, the use of entanglement to build better clocks and sensors. Entangled particles can outperform classical systems when it comes to measuring tiny changes in time, gravity, and magnetic fields. Atomic clocks, already accurate to within billionths of a second, could be improved using entangled atoms, leading to GPS so precise it could detect tectonic shifts or even monitor your heartbeat from orbit. Creepy? Yes. Useful extremely. Historians still argue whether this rise of quantum tech marks the third quantum revolution, the first being quantum theory, the second being things like lasers and semiconductors. But one thing's clear: entanglement has escaped the thought experiment box. It's no longer just something for midnight debates and cocktail napkins. It's hardware. It's protocol. It's something engineers are learning to debug. And all of this raises a new question, one that feels oddly intimate. If we can harness entanglement, if we can measure it, encode it, transmit it, use it to protect secrets and build machines, then what does that say about its nature? Is it still spooky? Or has it become part of our normal, like electricity or gravity, once magical, now mundane? You roll over and picture it. millions of entangled qubits flickering across server racks in quiet labs, photons darting down fiber optic cables, whispering their quantum keys, algorithms pulsing in wave functions. Somewhere, Schrödinger's cat is smug. The strangeness remains, of course. Entanglement still defies easy interpretation. It still messes with your sense of space, time, and reality. But now it's also useful. It has jobs. It pays rent. And that, more than anything, means it's here to stay. So you close your eyes again, listening to the steady hum of the quantum machines in the distance. Somewhere out there, a pair of particles spins silently, perfectly correlated, waiting to be measured, waiting to be used. Spooky action, now with a user manual. Your thoughts have settled into something soft now, like dust suspended in late afternoon sunbeams. The math has faded into the background, replaced by a slower, stranger question, one that physicists don't like to admit they think about, but they do. You do. Everyone does, eventually. Because if quantum entanglement is real and space and time are just maybe optional, then what if all of this is real, that is? What if we're living in a simulation, and quantum mechanics is just the backend acting buggy under load? You smirk, but you're not alone. This idea, the simulation hypothesis, isn't just a midnight dorm room joke anymore. It's been presented in earnest by philosophers, computer scientists, and even a handful of brave physicists. The logic goes something like this. If it's possible to simulate conscious beings in a computer, and if advanced civilizations can eventually run many such simulations, then statistically, it's more likely we're in a simulation than the base reality. If there are 10 billion simulated Earths and only one real one, guess where you probably are. And then, because your mind's already deep in the fog, someone brings up quantum entanglement. Maybe it's not a natural feature of the universe at all. Maybe it's a shortcut in the code, a clever trick to keep distant events synchronized without chewing up too much processor time. Entangled particles are instantaneously connected. Sure, maybe because they're referencing the same bit of memory in some grand cosmic database. Or maybe because the simulation engine isn't rendering the full state until someone hits measure. That sounds familiar, doesn't it? This is the darkly funny part of the simulation idea. It actually explains some of the weirdness of quantum mechanics. Wave function collapse. That's just the rendering system deciding what version of reality to commit to based on player input. The speed of light limit, a lag cap, entanglement, a way to maintain internal consistency between objects no matter where they appear in the rendered space. Quirky, definitely. Plausible, that depends on who you ask. One particularly eccentric theory, fringe, but not without charm, suggests that entanglement is what happens when two entities in the simulation are running off the same algorithmic seed. Change one, and the other updates immediately because the system isn't processing them separately. It's not physics, it's optimization. The universe isn't a machine, it's a program. In fact, some researchers have proposed experiments to test this. One idea was to look for digital compression artifacts in the behavior of high-energy cosmic rays. If reality is being computed on a giant grid, then there should be tiny telltale signs, like jagged pixelation around the edges of existence. So far, no dice. But absence of evidence isn't evidence of absence, as any good conspiracy theorist or cautious physicist will remind you. Historians still argue whether the simulation hypothesis is even worth discussing in serious scientific contexts. Many say it's untestable and therefore not science. Others argue it's a metaphysical shrug, no different than asking if the universe was created by a god, or if the laws of nature are just brute facts. But then again, quantum mechanics forces us to confront the idea that observation creates reality. And once you open that door, it's hard not to wonder who, Or what is doing the observing? There's also the uncanny way quantum mechanics seems to blend information theory and physics. Entropy, probability, entanglement, they all revolve around information, not matter, not motion, not force, just bits, patterns. The simulation crowd loves this. To them, it's proof that the fabric of the universe isn't particles or fields, it's code. The cosmos as a spreadsheet. But let's not get carried away. Even if we are in a simulation, what changes? Your socks still need folding. Gravity still pulls. Hearts still break and heal. Maybe the realness of a thing isn't about where it sits in the chain of simulations, but about how it feels, how it matters. If your dreams are simulated, but they still move you, are they any less real? You shift slightly under the covers. The quiet is deeper now. Outside, the world, real or otherwise, hums along, oblivious to your metaphysical musings. And yet the questions persist. If entanglement links particles instantly across space, and if measurement collapses states in a way that seems aware of future choices, then where exactly are the rules coming from? Who enforces the laws of physics when no one's looking? And if no one's looking, does anything exist at all? In this light, entanglement isn't just a scientific puzzle. It's a glitch, a clue, a shimmer in the matrix, or maybe just a reminder that whatever reality is, it's weirder than we're built to understand. So you breathe in, slow and steady, and let the thought drift. Maybe the reason entanglement feels so eerie is because we're brushing up against the edges of the rendered world. Not because it's fake, but because we're part of it, deep inside it, writing it with every act of observation. And that's not a bad thought to fall asleep to. The idea that you're a participant in reality's unfolding, that your choices, your curiosity, your quiet questions at 2:43 a.m., they matter. Even if you don't know how, even if no one ever tells you why. Because whether this is base reality or a hyper-advanced simulation running on a universe-sized GPU, you still get to choose what story you tell yourself. And tonight, maybe that story starts with two particles, far apart but inseparable, whispering through the code of the cosmos. You're so deep into the quantum fog now that time itself feels optional, like socks in summer or replying to that one email. You've learned that entangled particles don't care about distance. You felt the universe wink as it collapses a wave function the moment you observe it. And now you're ready, maybe, to tiptoe into one of the strangest questions of all. What if the future influences the past? It sounds backward, and it is. But in the world of quantum physics, backward isn't necessarily wrong. This idea has a name, retrocausality. It suggests that effects might sometimes happen before their causes, that your choice to measure something now could reach back and shape what happened then. Not just in a poetic sense, like your decisions define who you've always been, but in a literal, mathematical, time-defying way. The notion isn't just some stoner daydream either. It has serious voices behind it. One of the most famous comes from physicist Yakir Aharonov, who proposed the two-state vector formalism in the 1960s. In his framework, a quantum system isn't just guided by conditions in the past, like we usually assume, but also by conditions in the future. The present becomes a kind of midpoint, where past and future boundary conditions converge to determine what happens. It's like watching a movie where both the beginning and the ending determine how the middle plays out. The plot thickens, but also rewinds. This isn't just metaphysics wrapped in fancy equations. Some experiments have flirted with retrocausal interpretations. Delayed choice quantum eraser setups, for example, appear to allow measurement choices made after a photon has hit a detector to influence how it behaved earlier. You don't change the past outcome, exactly, but you seem to change the context in which it was recorded. The experimenter's future decision rewrites the meaning of a past event. And that's deeply weird. Because if the universe is allowed to do that, if it's allowed to adjust earlier events based on later choices, then what becomes of free will? What becomes of determinism? Are we truly deciding anything, or are we just fulfilling the endpoint of a process that's already complete? Fringe detail incoming. In the 1990s, a handful of researchers even proposed that certain quantum anomalies might be messages from the future. One idea, mostly dismissed but never quite buried, was that neutrinos might carry information backward through time, subatomic messengers from events that haven't happened yet. It sounds bonkers. It is bonkers. But when your field allows particles to exist in superposition, affect one another instantly, and collapse reality when observed, bonkers is kind of the default setting. Of course, not everyone buys into retrocausality. Historians still argue whether the entire idea is just a clever math trick. Many interpretations of quantum mechanics are time-symmetric, meaning they don't distinguish between forward and backward, but that doesn't necessarily mean cause and effect reverse. In practice, the arrow of time, the one that flows from breakfast to bedtime, still seems to hold. Eggs still crack. Tea still cools. Your to-do list still gets longer, never shorter. But some physicists insist that time symmetry deserves more respect. They point out that most of the fundamental equations in physics don't care about direction. They work just as well forward as backward. It's only entropy, the measure of disorder, that gives time a preferred direction. Maybe, they argue, the universe is symmetric after all, and it's only our limited experience, our perspective as heat-generating meatbags, that makes time feel one way. This idea gets especially juicy when paired with entanglement, because if entangled particles can instantly affect each other across space, and if time is just another dimension to mess with, then maybe, one measurement really does reach both across space and time. Perhaps what we call collapse is just the final handshake in a loop that includes both past and future. And then your brain quietly folds in on itself. You're not alone in feeling overwhelmed. Richard Feynman, one of quantum theory's most legendary figures, once said, "I think I can safely say that nobody understands quantum mechanics, and that includes retrocausality." Most physicists are still cautious, very cautious about the idea. There's no definitive experiment that confirms it, and until there is, it remains a beautiful, unsettling hypothesis, a crack in the glass, a whisper from the end of the movie. But you can't stop thinking about it, not just because it's wild, but because it reframes so much. What if entangled particles coordinate not through a superluminal signal, but because they're both influenced by some shared future condition? What if the measurement outcomes aren't determined when we think they are, but in a place outside time, where when doesn't even make sense? It's not comforting, but it is elegant. Retrocausality takes the sting out of non-locality. It says, no, particles aren't talking to each other across the universe faster than light. Instead, they're both responding to something deeper, something timeless. Maybe that's more palatable, or maybe it just shifts the weirdness around without reducing it. Either way, the story doesn't end here. Because while we can't send messages into the past, and while the best experiments still obey the normal arrow of time, the quantum world has made one thing very clear. Causality isn't as absolute as we once thought. It's more like a story told in reverse, or a dance where no one remembers who led. So as you finally exhale and let yourself fall fully into the dark, you imagine time not as a line but as a loop, a spiral, a field. You imagine your choices reaching backward as well as forward, not to change the past but to complete it, to fulfill something already woven into the shape of things. Because maybe time isn't a one-way street, maybe it's a conversation. And you're still mid-sentence. By now, you've let go of most of what you used to believe about space and time. Measurement collapses reality, causality might work in reverse, and two particles separated by light years still act like they're sharing a secret diary. But tonight, you find yourself wondering something even bigger, maybe the biggest sleep-breaking question of all. If information really can travel faster than light, or if it doesn't need to travel at all, what does that say about the structure of space-time itself? You've always been taught that space and time are the stage on which physics happens, a cosmic arena. Time ticks forward, space stretches in three neat dimensions, and things happen within that framework. But what if the stage isn't real? What if the actors are making up the rules as they go, and the stage only exists because they're interacting? That's the strange implication of entanglement, and the even stranger direction some physicists are now exploring. The question is no longer, can information travel faster than light? But is distance even a meaningful concept at the quantum level? Because entanglement seems to laugh in the face of distance. It doesn't diminish with separation. It doesn't slow down. There's no gradient, no drop-off. Two entangled particles can be centimeters apart or galaxies apart, it doesn't matter. Their connection is instant, undiluted. That kind of behavior isn't just weird, it's unspatial. It's as if space isn't there between them. So maybe some physicists argue space is emergent, not a fundamental feature of the universe, but something that arises from deeper rules, like temperature emerging from the jiggling of molecules. In this view, space, and even time, aren't the starting point. They're what happens after entanglement. Enter one of the most whispered about ideas in modern theoretical physics. Entanglement builds space-time. The idea is that the geometry of the universe, the whole fabric of space and time, might be woven together by quantum entanglement. That the reason things are close or far from one another is because of how entangled they are. No entanglement, no connection, no space. One of the first serious nudges in this direction came from studies in black hole thermodynamics. In the early 2000s, researchers discovered a deep connection between the amount of entanglement in a quantum system and the curvature of the spacetime that system was embedded in. It led to bold speculation. Maybe gravity, spacetime, and geometry aren't the foundation of physics at all. Maybe they're byproducts of entanglement, ephemeral, emergent. And if that's true, then trying to understand faster-than-light information transfer is like trying to run faster in a dream. You're asking the wrong question. The particles aren't communicating across distance. They're just not separate to begin with. Distance, in this model, isn't real in the way you think it is. It's a shadow cast by something deeper, quantum structure that doesn't live in space at all. This isn't just poetic physics. In 2013, theoretical physicist Mark van Ramsdonk wrote a now-famous paper suggesting that entanglement is not just a curious side effect of quantum mechanics. It's the glue that holds the universe together. The more two regions of space are entangled, the more connected they are geometrically. Sever that entanglement and space itself might tear. It's like saying a friendship doesn't just link two people, it creates the sidewalk between their houses. Of course, these ideas are still speculative. Historians still argue whether this emergent spacetime concept is a valid way forward or a philosophical detour. Some physicists love the elegance. Others point out that we don't yet have a full theory that connects entanglement to Einstein's equations in a predictive way. But experiments are slowly catching up. Studies of quantum simulations and entanglement entropy in particle systems hint at a deeper order, one where space isn't a given, but a result. One quirky experiment you'll enjoy. In 2022, researchers at Google's quantum computing lab simulated a tiny toy model of a wormhole using entangled qubits. It wasn't a real wormhole, not in the interstellar sense, but it acted mathematically like one. Information entered on one end, disappeared from the system, and reappeared on the other side as if it had passed through a tunnel in spacetime. It was small, crude, but it hinted that maybe, just maybe, we can build space-like behavior out of pure entanglement. So now you lie there very still and wonder, if space can be built from quantum links, what does that make you? Your body, your breath, your thoughts, they all exist within space-time. But if space-time is emergent, then so are you. Not in a mystical way, but in a deeply physical one. You are a structure arising from interactions, a node in a web of quantum correlations, not in space, but of space. And what about light speed? What about information transfer? Maybe those are just artifacts of a reality that only looks like a grid when you zoom out. Up close, down where the particles whisper and entanglement pulses, there's no distance to cross, no time to wait. The map breaks down, the road vanishes, the destination is already here. You picture it now, a universe not built on coordinates and clocks, but on connection. Entanglement as the true thread of existence. The deeper the connection, the closer things become, not in meters or miles, but in meaning. It's not about speed, it's about structure, not about travel, but presence. You don't need to move information if everything's already woven together. And that thought, so wild, so quiet, hums gently through your mind. The idea that the deepest level of reality isn't particles or forces or space, but relationships. That the cosmos is a tapestry, not a machine. A network, not a stage. And somewhere in that fabric, two particles, entangled, inseparable, continue their silent conversation. You've passed the point of no return now, slipping gently into the part of the night where the rules loosen and the edges of things get soft. You've let go of classical space, bent time into a loop, and even entertained the thought that spacetime itself might not be fundamental. And yet, there's still one fork in the road that refuses to stay quiet. The idea that when a particle is measured and its wave function collapses, it doesn't just pick one outcome, it picks all of them, each one in its own universe. Welcome to the disorienting, dazzling hallway of mirrors known as the many worlds interpretation. It's not exactly what you think. There's no dramatic pop as infinite Earths are born from every coin toss. No blurry copy of you sitting beside you on the couch eating slightly less buttery popcorn. It's subtler than that, but also more radical. Proposed by Hugh Everett III in 1957, an underappreciated genius who sadly died young. The many worlds interpretation says this: wave function collapse doesn't happen, ever. It's not a real process. Instead, the wave function continues to evolve according to the Schrödinger equation, smoothly, deterministically. And when you observe a quantum system, you don't force it into a definite state. You split. You become entangled with the system, branching off into a version of reality where you saw that outcome. Somewhere else, another version of you saw the other one. It's not the universe making a choice. It's you and the universe splitting into paths. So imagine an entangled pair of particles. You measure one here on Earth, and instantly you know the state of the other, which is drifting alone through interstellar space. From the outside, it looks like the measurement here affects the distant one. But in many worlds, that connection isn't some magical superluminal influence. Instead, the act of measurement entangles you with the particle's state. In the version of reality where you measured spin-up, the distant particle is spin down. In the other branch, it's the opposite. Each outcome exists. You only experience one. No faster-than-light messaging. No spooky action, just branching. It's a seductive explanation, especially for those who can't stomach the idea of wave function collapse being real or the universe behaving randomly. Many worlds preserves determinism. Everything follows the rules. Every possibility plays out. And yet, your conscious experience only follows one thread, just one story, unfolding quietly in your skull while an infinite number of you watch slightly different versions of the same movie. There's something cozy about that, and something terrifying. It also brings new complications to entanglement. If every possible measurement outcome occurs in a different branch, then how do the distant outcomes still correlate perfectly? Why, in every branch, does it always appear that the two particles are anti-correlated, even though nothing instantaneously changed? That's the beauty of the math. It preserves the statistical structure. Even across branches, the entangled particles keep their ghostly agreement. There's no need for faster-than-light signals. No need for collapse. The branching is the resolution. But still, it's a lot to swallow. An infinite number of universes being created every second. You can see why it didn't catch on at first. Everett's paper was mostly ignored in his lifetime. Only decades later did physicists begin to take it seriously, partly out of desperation, partly because it just wouldn't go away. It kept explaining things cleanly, consistently, spookily sensibly. Historians still argue whether many worlds is truly scientific or just metaphysical sleight of hand. After all, if you can never visit or observe the other branches, are they real? Do they matter? Some say it's just a useful model, not a statement about reality. Others say it's the most straightforward reading of the math. No collapse, no hidden variables, just unending, unobservable multiplication. Here's a fringe gem for your pillow. In the 1980s, an eccentric physicist named David Deutsch argued that many worlds could explain not only quantum mechanics, but the nature of consciousness itself. In his view, the mind is constantly branching, constantly splitting across decisions, and our feeling of free will is just our awareness navigating one version of countless possibilities. In another world, you skipped this podcast and went to bed early. In another, you became a theoretical physicist and ran this episode yourself. You're everywhere and nowhere. Quantum computers, interestingly, are sometimes described using the language of many worlds. Each qubit explores a vast landscape of possibilities, performing calculations across an enormous space of outcomes. Some people explain this as the quantum machine, calculating in many worlds at once, though others roll their eyes at the metaphor. Still, the imagery sticks. It's hard not to imagine the processor surfing down a branching tree of universes, finding the leaf with the answer you want. But does any of this help us understand entanglement better? Maybe. In a many worlds view, entanglement becomes less like a bridge and more like a constraint. Each measurement branches you into a version of the world consistent with the other measurement. You're not coordinating across space. You're walking a shared path through the tree. Every observer sees results that match because the only branches you can follow are the ones where they do. No messages, no paradox, just structure. Still, the cost is steep. You must accept that every outcome exists, that every version of you, every joy, every failure is out there, unfolding, eternal. It's a lonely thought or a liberating one depending on your mood. You shift under the blanket and close your eyes, picturing a world where you turned left instead of right, where you kissed the person, where you took the risk. All those universes, spinning outward, forever entangled like particles that never quite let go. And maybe that's what entanglement really is. Not communication, not causality, but correlation across possibilities. A cosmic agreement signed in probability, honored in every world. Even this one. By now, your brain should be gently steaming, but there's one last border we haven't crossed, and you can feel it looming, humming just out of reach. We've watched particles tangle across light years. We've asked if spacetime itself is built on invisible quantum scaffolding. We've even imagined entire universes splitting from a single spin measurement. But now comes a more personal and frankly weirder question. What if consciousness itself is entangled? You feel that little shiver, don't you? Because it sounds ridiculous, pseudo-scientific, like something scribbled on the back of a napkin at a wellness retreat. But don't worry, we're going to walk carefully. Because buried under the incense and awkward text talks, there's a faint glimmer of something real, or at least something physicists can't entirely dismiss. Not yet. Start with the obvious. Quantum mechanics is a theory about measurement, and measurement always involves an observer. That doesn't mean a human necessarily. It could be a Geiger counter or a piece of lab equipment, but at some point something has to register the result. That's where the wave function collapses. That's when the particle makes its final choice. And for decades, scientists have argued over what exactly counts as an observer. Is it a conscious mind, a thermometer, a cat? This opens the door, just a crack, for something deeply unsettling. Maybe consciousness plays an active role in the formation of reality. One of the earliest proponents of this idea was none other than Eugene Wigner. Back in the 1960s, he proposed that consciousness itself might be necessary to collapse the wave function, that the act of knowing something, of being aware, was what finalized the outcome. He even imagined a twisted variation on Schrödinger's cat, in which the entire universe remains in superposition until a conscious mind checks the box. It's since been dubbed the Wigner's friend thought experiment, and it's every bit as weird as it sounds. But does this mean human consciousness is entangled with quantum systems? That your thoughts can influence reality just by existing? Well, not exactly. Or at least not in any way we can measure. But some fringe researchers, not the YouTube mystics but actual credentialed physicists, have explored whether entanglement might occur at the level of the brain. Could neurons or the structures within them become quantum coherent? Could entanglement play a role in memory, intuition, or awareness? Most neuroscientists will tell you no. The brain is warm, wet, noisy, terrible conditions for maintaining delicate quantum states. Entanglement typically requires cryogenic temperatures and extreme isolation. The idea that your brain is hosting a quantum computer between coffee and emails sounds absurd. But then there's the nagging exception: microtubules. In the 1990s, physicist Roger Penrose, yes, the Nobel-winning black hole guy, and anesthesiologist Stuart Hameroff proposed a bold theory: that consciousness arises from quantum processes inside microtubules, tiny scaffolding structures found in neurons. According to their orchestrated objective reduction model, these microtubules might support quantum coherence, allowing entangled states to form and persist within the brain, if only for brief, flickering moments. The idea was immediately controversial, still is. Most mainstream scientists view it with deep skepticism, but it hasn't entirely disappeared. In fact, some recent studies have suggested that microtubules might exhibit certain resonance behaviors, oscillations that could, under the right conditions, hint at coherence. Not proof, not even close, but enough to keep the door open a sliver wider. And here's a twist to lull you into confusion. Even if the brain isn't using quantum entanglement, it might still be entangled with the systems it observes. Because if you are part of the universe, and of course you are, then your consciousness is entangled with the particles, fields, and wave functions around you. Not in a mystical sense, but in the cold, statistical language of physics. Every time you measure a system, you become part of its state. You're not just watching reality, you're woven into it. So what happens when two minds become deeply entangled with each other? Do they form correlations that go deeper than classical understanding? Could empathy, intuition, or sudden insight be signs of shared quantum structure? These are questions science isn't ready to answer. Not because they're invalid, but because we don't yet have the tools to ask them properly. Historians still argue whether the role of the observer in quantum mechanics was ever meant to include consciousness, or if that idea was tacked on later by a generation of physicists with too much free time. Bohr, famously vague, said only that observation played a key role. He never pinned down whether it required a mind, a machine, or merely a record. But the gap he left has been filled, repeatedly, by dreamers, mystics, and theorists who wonder if our very thoughts might be written in the language of quantum logic. There's even a fringe proposal floating around that group consciousness. The collective awareness of large populations might behave like a macroscopic quantum system. Researchers in the Global Consciousness Project have tried to detect patterns in random number generators during major world events, suggesting that collective human emotion might affect probability. It's not taken seriously by most physicists, but the experiments continue quietly, year after year. And so you return to the thought, if consciousness is part of the quantum process, what does that make you? Not just an observer, but a participant, a variable, entangled not just with what you see, but with how you see it. You roll onto your back, eyes closed, and picture the entangled web of everything. Stars, neurons, photons, feelings. Not connections of energy or matter, but correlations. Shared outcomes. Cosmic empathy baked into the machinery of reality. Maybe consciousness isn't just along for the ride. Maybe it's one of the entangled threads, not the cause of collapse, not the driver of fate, just another part of the pattern, shifting, shimmering, watching itself unfold. And in the silence of this thought, you are very still. So after all this deep breath physics, your calm stroll through the collapse of space, time, and classical thought, you probably think it can't get weirder. But there's one more door in the hallway, one more theory scrawled on the edge of credibility, propped up somewhere between quantum mechanics and the blinking lights of Area 51. Yes, tonight, very gently, you step into the intersection of entanglement and alien technology. Welcome to the part of the story where quantum physics meets the UFO people. First, let's be clear. The mainstream physics community does not accept that quantum entanglement is being used by aliens to zip around the galaxy or beam messages into your microwave. But, and here's the fun part, there are just enough strange overlaps between cutting-edge physics and reported UFO behavior to make a few curious minds sit up and say, wait, what if? It starts, as all good conspiracy-adjacent theories do, with a mystery. Sightings of unidentified aerial phenomena, UAPs, as they're now officially called, have described craft that appear to defy known laws of motion. Objects that accelerate from 0 to thousands of kilometers per hour instantly, that make 90-degree turns at speeds that would liquefy any pilot, that vanish into thin air without sonic booms. In short, objects that behave as if they're not playing by the rules of spacetime. And here, where the entanglement speculation creeps in, what if these aren't just faster-than-sound aircraft, but systems unbound by locality? What if their propulsion or their communication systems don't rely on normal cause and effect physics at all? What if they operate using entanglement? The idea goes like this. If you could harness quantum entanglement, not just to link particles but to manipulate that linkage, then maybe you could create communication systems that work instantly across space. Or even better, navigation systems that let you tunnel from one point in space to another without crossing the space in between. A kind of quantum jump, guided by probability, not propulsion. It's completely speculative. It's also very fun to think about at 2:14 a.m. A few fringe physicists, often working on the blurry edge of credibility, have proposed that an advanced civilization, one millions of years beyond us, might have figured out how to use entanglement in ways we can't yet imagine. To them, entanglement isn't a curiosity to be preserved in lab experiments. It's a structural feature of reality that can be engineered, like gravity or magnetism. If space is emergent, and if entangled systems create the fabric of space itself, then manipulating entanglement might literally reshape the map. The craft wouldn't be flying through space, they'd be rewriting it as they go. It's a seductive idea, especially when you remember that entanglement is scale agnostic. It doesn't weaken with distance. If there is some unknown method of using it to coordinate action across light years, even if not for communication in the traditional sense, then maybe what looks like faster-than-light travel is actually no travel at all. Of course, the big problem here, besides a complete lack of experimental support, is that entanglement still obeys the no-signaling rule. You can't use it to send classical information faster than light. Every experiment to date agrees. And even the most generous physicists will tell you, if aliens are doing something with quantum entanglement, they're not doing it with the kind of physics we understand. Still, speculation continues. One of the strangest intersections came in a declassified U.S. Department of Defense document, which mentioned the theoretical possibility of using entanglement-based communications in deep space. No tech, no hardware, just blue-sky ideas on paper, but it sparked rumors, forums, late-night Reddit threads. Some took it to mean the government knew more than they were admitting. Others saw it as a sign that the science was catching up with the folklore. Historians still argue whether the modern obsession with alien tech is just Cold War anxiety dressed in quantum clothing, or if it reflects something deeper, a growing intuition that the universe is stranger than our current models allow. That maybe our understanding of space, time, and information is only a shadow of something bigger, something that advanced civilizations could already be surfing like a wave. And here's a fringe detail to curl your toes. Some UFO researchers claim that certain sightings, especially those involving apparent telepathy or instant knowing, might be explained not by radio or sound, but by a kind of entangled cognition. That the beings, if they exist, don't speak because they're quantum linked with each other. That their minds operate not in isolation, but in quantum superposition with one another. It's wild. It's unsupported. It's also oddly symmetrical, with the strangest corners of our own physics. You lie back now and imagine an alien ship, not a clunky saucer, but something soft and luminous, bending the rules as it flickers across space-time. Not moving, but emerging. Not flying, but changing what place means. Its technology wouldn't have wires. It would have wave functions. Its systems wouldn't hum, they'd resonate. Each part entangled with every other as if the craft was one unified organism of possibility. Like a particle, like a thought. And maybe that's the dream buried under all this speculation. Not that aliens are using entanglement, but that we might. Someday, that quantum technology might let us step outside our box of cause and effect, of distance and delay. Not to escape Earth, but to understand it. To reshape our ideas of communication, presence, and identity. To stop thinking of things as here or there, and start thinking of them as together. Because in the end, that's all entanglement is. A promise between particles that no matter how far they go, they'll never really be apart. And if aliens have figured that out before us, well, fair enough. You've traveled far now, so far that the usual landmarks of science and sense have all but vanished in the rear view. Space, emergent, time, unreliable, causality, optional. You've entertained the possibility that consciousness might be entangled, that aliens might surf quantum pathways, and that measurement might tug on the threads of destiny. And now, just when you think there's nowhere stranger left to go, you step, quietly, barefoot, into the shadowy, shimmering world of string theory, where particles become loops, dimensions multiply, and entanglement gets tangled in an entirely new way. Let's start small. At the most basic level, string theory proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings of energy. Each vibration corresponds to a different particle, like musical notes played on the same instrument. These strings are absurdly tiny, far beyond what we can currently observe, but their behavior might explain the forces in particles we see. Gravity, electromagnetism, the strong and weak nuclear forces. All unified in theory, by the music of these invisible strings. But string theory didn't just invent a new way to look at particles. It also pulled open the curtains on something else: extra dimensions. Not just the 3 spatial dimensions and one of time that we're used to, but 6 or 7, depending on the version, extra dimensions curled up tightly at every point in space. These aren't dimensions you can visit or point toward. They're compactified, folded into complex shapes called calabi, Yau manifolds. Picture space as a bedsheet, but each thread of fabric is a tiny, hidden labyrinth of curled geometry. That's where the strings dance. And here, where things get slippery, in this landscape of hidden geometry and vibrating strings, entanglement might not just be a feature. It might be the glue holding everything together. Some physicists believe that entanglement isn't just a phenomenon that happens within spacetime. It might actually create spacetime itself. That idea, which seemed wild even by string theory standards a few years ago, is gaining traction. A pivotal clue came from the study of black holes, specifically from an idea called the holographic principle. This principle, championed by theorists like Juan Maldacena, suggests that everything inside a volume of space can be described by information encoded on its boundary. Like a hologram, a 3-dimensional image projected from a 2-dimensional surface. In string theory, this concept was formalized as the AD-SCFT correspondence, which links a bulk space, like the inside of a box, to a boundary theory that lives on the surface of that space. In this model, gravity and spacetime exist inside the bulk, while quantum fields live on the boundary, and the two are mathematically equivalent. Still with me? Good. Now here, where entanglement enters the holographic chat. In 2006, 2 physicists, Mark van Ramsdonk and Shinsei Ryu, proposed that the amount of entanglement between different regions of a quantum field determines the geometry of the corresponding bulk space. Less entanglement, the space pulls apart. More entanglement, the space holds together. In other words, entanglement creates spacetime, not metaphorically, literally. This led to a now famous catchphrase among theoretical physicists: ER equals EPR. It's shorthand for a speculative but surprisingly sticky idea that Einstein-Rosen bridges, aka wormholes, or ER, are equivalent to Einstein-Podolsky-Rosen entanglement, EPR. The conjecture suggests that if 2 particles are entangled, there may be a tiny, non-traversable wormhole connecting them, an invisible thread of geometry linking their states. Not a passageway you can fly through, but a geometric expression of their correlation. It's a deeply poetic thought, one Einstein might have reluctantly loved, that the very spooky action at a distance he once mocked might be woven from the same material as wormholes, the speculative shortcuts through spacetime that he helped theorize decades earlier. Historians still argue whether the ER equals EPR conjecture has any experimental implications, or whether it's just elegant math and good PR. But it captures a growing suspicion that entanglement and geometry are not just related, they may be the same thing viewed from different perspectives. In this view, a pair of entangled particles aren't breaking the rules of locality, they are simply connected in a dimension we can't perceive. To us, they appear distant. But in the deeper structure of string theory, they might be neighbors. Of course, this raises some deliciously uncomfortable questions. If entanglement is geometry, then what does that make you? Your body, your memories, your thoughts, are they just tightly curled strings, vibrating in higher dimensions, held together by webs of correlation? Is your identity a shape in entanglement space? And if so, what happens when those threads fray? Do you drift apart? Do you unfold? There's also the unsettling implication that information, the currency of quantum mechanics, is the true foundation of the universe. Not mass, not charge, not even energy, just information flowing through entanglement, shaping the geometry of reality like an unseen sculptor. It's not clear whether this means the universe is a simulation, a computation, or something else entirely. But it is clear that string theory is beginning to treat spacetime not as the stage, but as a story told in data. Here's a fringe twist to dream on. In some speculative models, it's possible that black holes, those mysterious regions of warped space and no escape, are not singularities at all but tangled bundles of strings. They're event horizons, not boundaries of space but limits of information flow. And their evaporation over time through Hawking radiation might be the universe slowly unbraiding the knot. In that sense, entanglement isn't just spooky, it's cosmic housekeeping. So you lie there now in the gentle dark and picture reality not as a thing but as a rhythm, a pattern of correlations. You imagine particles as knots of vibrating string, space as the warp and weft of entanglement, and yourself, soft, sleepy, as a ripple in that fabric. Maybe the universe is a loom. Maybe the threads are infinite. But in every loop, every twist, every resonance, one thing remains true. The closer things are entangled, the closer they are in meaning, even if they seem impossibly far apart. And now, slowly, softly, you reach the end of the thread. You've wandered through quantum fog and floated in timeless space. You've watched particles speak without sound, felt the strange tug of retrocausality, and peered into theories so abstract they might as well be dreams. And now, as the lights dim and your thoughts stretch out one last time, you find yourself looking outward, way outward. Not at an experiment or a theory or a math problem, but at the universe itself. Because what if, just maybe, the entire cosmos is entangled? It's not just a poetic idea. It's a real question now, one that cosmologists and quantum physicists have started to take seriously. Because if entanglement isn't limited by distance, and if it's as fundamental as many suspect, then perhaps the early universe, tiny, hot, dense, was one perfectly entangled object. One quantum state, smooth and whole, without separation or locality. And maybe, as it expanded, that entanglement didn't vanish. Maybe it just got stretched out. The idea isn't as far-fetched as it sounds. The early universe was governed by quantum laws, after all. The inflationary model, the theory that space itself underwent a burst of exponential expansion shortly after the Big Bang, says that tiny quantum fluctuations were blown up into the seeds of all the structure we see today. Stars, galaxies, clusters, they all began as quantum ripples. But those ripples didn't arise independently. They came from a single field, a single process. Meaning they were correlated, entangled. And those entanglements might still be here, echoing in the cosmic microwave background, whispering in the large-scale structure of galaxies, maybe even shaping the flow of time itself. Some researchers now propose that the observable universe isn't a patch of disconnected particles, but a giant web of entanglement, a single wave function, still humming after all these billions of years. There's a beautiful symmetry to that. The idea that everything, every quark, every light beam, every cell in your sleepy body is part of one giant, ongoing quantum state. It doesn't mean you're psychically linked to dolphins or that your thoughts can collapse a galaxy's spin. But it does suggest that separateness, true separateness, might be an illusion. Because in quantum mechanics, when two systems are entangled, they can't be described independently. Their states are linked. Their properties emerge together. If that's true of the universe itself, then what you do here might matter more than you think, not in a moral way, but in a physical one. You're not isolated. You're not disconnected. You're part of the pattern. Some scientists have even asked whether the reason the universe appears so coherent, so law-abiding, so finely tuned, is because it's still partially entangled with itself. That the laws of physics we observe are a reflection of underlying quantum constraints on the entire cosmic state. The idea is speculative, of course, but it's gaining traction, especially in studies of quantum cosmology, where researchers try to reconcile the expanding, dynamic universe with the fundamentally static, probabilistic world of quantum mechanics. Historians still argue whether this view of a globally entangled universe is necessary, or just a byproduct of over-extrapolating. Some say it's more philosophy than physics. Others believe it points toward a deeper unity, a post-classical model of reality where the whole truly is more than the sum of its parts. And now for one last fringe detail. Softly now, no need to panic. In certain versions of the multiverse hypothesis, entanglement doesn't just connect particles within our universe. It connects across universes, like a great web stretching beyond space and time, linking not just stars and atoms, but entire realities. Some researchers have tried to model this using so-called quantum multiverse formalisms, where each universe shares entangled roots with others. The outcomes we observe in this universe might be statistically constrained by events in others. Not influence, not control, just shared origin. It's not testable, not yet, but it offers one final layer of awe. Because if the universe is entangled with itself, and if the multiverse is entangled too, then reality is not just connected, it's fundamentally inseparable. So you lie here now, wrapped in blankets and half-formed thoughts, and the cosmos lies wrapped around you, quietly humming in its own probabilistic way. You are not floating in space. You are of space, entangled not just with someone across the world or a photon in a lab, but with the shape of the universe itself. And maybe that's the real heart of entanglement, not speed, not distance, not information, but relationship. A bond that doesn't weaken, doesn't fade, doesn't care about miles or seconds. A connection that says, we came from the same place. We are part of the same process. That's what entanglement is. That's what you are. That's what everything is. And now, here at the edge of thought, you begin to soften. The tangled pathways of entanglement stretch behind you like golden threads fading into mist. No more questions for tonight. No more paradoxes. Just a quiet knowing suspended in the dark. You can still feel them, those particles, those possibilities, spinning somewhere beyond your awareness. Linked, not by wires or force, but by understanding. Not distance, but design. The universe isn't shouting answers. It's humming lullabies in the gaps between measurements. Your mind, once darting between timelines and interpretations, slows into longer breaths. Time settles back into its familiar rhythm. Space regains its quiet boundaries. You let go of faster-than-light influences and wave function collapses. You allow them to dissolve into sleep, still unresolved, still beautiful. Nothing has to be proven here. Nothing has to be solved. The cosmos doesn't demand comprehension, only attention, only awe. You did that tonight. You walked the invisible bridge between science and story. You listened. You wondered. That's more than enough. So now you rest. The equations fall silent. The photons dim. And all the entangled things, all the distant, dancing twins across space and time drift back into the fabric that wove them. Still connected, still spinning, still yours.